Yes, ma'am.
Yes, sir.
Okay. So today we are going to talk about hierarchical cascaded processing. So if you remember our previous discussion, there we have seen some graphs and some discussion were there to emphasis on the fact that according to the present literature, whatever types of embedded processors we have, and on top of them always when we are going to implement this always on devices, they are having some kind of energy bottleneck. That means we have seen one graph which shows that whatever requirement we have in terms of this CNN architecture to implement one CNN related ML processing on these kind of always on or mobile devices. In mobile devices, still there is some feasibility, but for always on devices, the this energy bottleneck is there. So we cannot realize whatever you have we have discussed those type of CNN structure, CNN based learning and prediction. We cannot actually implement in this always on device. We also talked about that we are not actually going to at this stage we are not going to realize the whole CNN learning as well as the prediction part. We are just focusing on the prediction part because learning part we as we have seen has a lot, even lot more steps like propagation, that kind of costly things. So at this point we are not thinking of affording those things in, always on devices. Just we will be whenever we are talking about this embedded ML, as of now, we are concentrating on that prediction part only. Okay. In the prediction part, since we have this kind of energy bottleneck, we have to think in which part we can optimize, in which part we can improve. The first thing is that we have to think about energy efficient algorithm. That means that this ML algorithm, the ML compute related computation we are doing, that algorithm we have many existing algorithms in literature, but how we can make them energy efficient, what modifications we will bring into them so that it can be more energy efficient, and it can be as per to our always own devices requirement. Okay. So we will focus in terms of algorithm, core ML algorithm. We have seen some parts of hardware. We talked about DSP processors in detail, and we have seen how this embedded processor can be meaningful in terms of our ML. I mean, this type of CNN multiply accumulated accumulation related operations to realize them efficient. Now, how to make them efficient, energy efficient? To realize again, they say CNN processing. And the third one, developing more intelligent systems that can exploit application level characteristics to increase energy efficiency. Now, these algorithms, maybe some part of hardware we will discuss later, will be more generic. In the we will start from this most maybe some most easiest, most top level solution. If we go this way, if you think about a hierarchy, we have some application. For that, we have designed or we have chosen some algorithm, and that algorithm we have implemented on a particular hardware. So that is the flow. So that's why we are starting from this application. So whatever solution we are going to discuss today, this cascading technique, it may not be suitable for all type of ML applications or for all type of ML related solutions when you are going for embedded ML also. But we are talking about few specific type of applications and how their specific characteristics can be exploited to make them more energy efficient. Okay. So before that, before we are going to the actual type of application and we will discuss with some examples, first we will talk a bit about how this energy and computation, how they are related. When we are talking about energy, maybe energy, we can start the discussion from power consumption, and from there we can directly relate with energy. So when we are talking about the dynamic power consumption, when some algorithm, some process and execution in your embedded processor or any processor, whatever it may be, in any processor, the dynamic power consumption originates from the activity of logic gates inside a CPU. It may be CPU, central processing unit, it may be the processing unit of your microcontroller. What happens when you are doing, let's say in the CNN computation, you are multiplying the filter weights with your input matrix. So you are basically doing some multiplication. Whereas in pooling, you are doing some addition. Now this multiplication, from your general mathematical concept, you know that is more costly than in terms of, I mean, in comparison to the addition. So what is the, so when you are doing basically the multiplication, this multiplication is actually getting mapped to your underlying hardware. There you have the multiplication unit, or in case of multiply and accumulate unit, that is getting activated, and you are using repeatedly that mac unit in your maybe in your underlying process. So those logic gates, when we are talking about this multiplier, basically those are some, those are developed from some underlying logic gates, and gate or gate, those type of logic. So these logic gates, they get activated. So whenever you are doing any processing, how many logic gates are getting activated? Based on that, we tell some operations, some applications are power hungry, some applications are, we tell that okay, they can be, deployed, they can be executed in less power scenario. So that is the concept. If you understand that one, then you can understand whenever you are executing, whenever you are implementing, whenever you are working with any operator, like in this end, you are multiplication, addition, those are the operators. Some energy is related with that operator. Okay. And here, if you are thinking that this EN is the total amount of energy consumed related to one operator N, like for example, you are writing a C code, you are writing addition, subtraction, multiplication, anything. So those are one operators, C operators. I think all of you may know. Now these operators, whenever they are actually you are implementing, you are what to say, executing some algorithm with the help of that operator, they are underlying activating some logic gates, and that way they are actually consuming some amount of power, or they are actually there is some kind of energy consumption, some amount of energy consumption related to that particular operator. And when you are calling that operator maybe n times, this is straightforward, your total energy is this, et is your total energy. So that way I think you got some idea how, when we are talking about more energy requirement, less energy requirement, what does it mean actually. Now if you go in detail, if this mn is a number of executions of a particular operator n, this mn will be maybe and this enm, this is the energy required for a particular operator. So this is again the total energy requirement to execute this particular operator mn times, mn times. Now when we are talking about this is for a simple operator, this is for a simple operator. Okay. But when we go for complex processors, these simple operators, now it may not happen that you are only using this type of simple operators. For complex operators, it may happen they are using in turn some simple operators, and their activity can be better realized not a single instruction but multiple machine instructions. Okay. So So basically, multiple machine instructions, they are clubbing together and they are getting used when you are actually using one single operator. Then we have to map the energy consumption related to a particular machine instruction and the number of that machine instruction you are calling, that is the INM. The together actually this summation is giving you the idea of energy requirement of a particular operator. Then this particular operator, how many times you are using, and that is giving you the amount of total energy. Okay. So is it clear that why we are talking about this suddenly about power consumption and energy when we are talking about some amount of computation? Is it clear? Any doubt? Okay. Now we will come to our machine learning discussion. Okay. We have some applications. We will see what type of ML algorithm we are using there, and we will see what type of optimizations we will make to that ML algorithm so that we can gain better energy efficiency. Okay. And the solution is here, building a functional hierarchy. We'll come step by step with some examples. Just first see what is written, then we will go with the example. So how we are talking about exploiting some application level characteristics. How we are doing that? We are doing that by building a functional hierarchy optimized for system level energy efficiency. Separate blocks with increasing functionality and cost are concatenated. Hierarchy is more efficient than a single stage system. We will see with some experimental results. And then in hierarchical cascaded systems, the overall computation cost of a classification is minimized without sacrificing the performance. So what we are pointing to in a nutshell, I have some operations to do. Okay. Like you are doing some image classification. Okay. As we have seen, we have some input matrix, and on top of that we are applying some filters, and we are applying some stride. We are actually sliding the filter, and then we are generating some feature map. Okay. This we have already discussed. Now, when you have a huge input matrix, you understand that, and you are doing everything, that this whole lot of multiplication in a particular stage, then of course there will be a huge number of multiplications. And from our previous slide, whatever we have discussed, we know the number of multiplications, I mean, the energy related to the per multiplication will be, at least in a straightforward way, you can think in this way, that the energy related to per multiplication will get multiplied with the number of multiplications required, and that will contribute to the total energy requirement of your functionality implementation. So this is your functionality implementation, that these huge multiplication you have to do. But when we are talking about hierarchy, in this idea, what we are telling is very simple. Okay, I will not do this type of multiplication in this whole input matrix. I will do in some partial parts. I will see whether that information is okay to pass on. If that is okay to pass on, then I will create a next level. Maybe this is level 1, then it is level 2. In this level 2, I will incorporate some more intense functionality related operations. So basically, the functionality related operations, we are dividing, we are chopping, and we are dividing in different levels of our hierarchy. And that way, we are forming this functional hierarchy. Okay. So let's take with an example this some contemporary state of the art detection. Okay, where you have seen this type of keyword recognition. Maybe when you are telling that, okay, Google, play this song for me, play a particular song. So when you are uh, giving this instruction to your OK Google device or your Alexa, you will see these are the examples of always on devices. But it is not that whatever you if you go closer to Alexa or OK Google, if you talk anything, it will not detect. You have to tell a particular keyword. That means Alexa, play. Show Harry Potter for me. So it is not first going to classify the movie name Harry Potter from its movie pool. What it is first doing, it is doing the keyword recognition. It is doing that, if this that Alexa or that OK Google is there already or not. If it is there, then it is taking the other parts of your instruction to the next level. And if it is not there, they are just ignoring everything. That means the whole, if that feature was not there, that hierarchy was not set up in their implementation. What was the possibility then? Whatever you were telling, they were detecting. According to that, they were trying to do some classification, and then there was no meaningful outcome was coming. But with this whole process, there was huge amount of computation going on. That is a wasted computation, we can tell. And when we are doing some computation, as you have seen, that computation is directly related to the some energy consumption. That's why there would have been some wastage of energy. Okay. So we are preventing that. We are for this always on devices. First, we are applying this keyword technology, keyword recognition. Okay, Google, Alexa, these are the keywords, and these are getting processed in your first layer of your hierarchy, and then some information is getting passed on. We will see that step by step. So the main idea is the first stage performs a very simple task with a low cost instead of powering on the full, more expensive functionality constantly. So full classification with all the keywords, with all the movie names, that is not going on within Alexa or within OK Google. This is this device you can only power on if you actually tell that with, if you can actually tell that keyword to that device. This reduces the average on time of a more expensive classifier considerably, and hence the global system energy consumption. So it is basically saves the energy without doing any unnecessary computation based on any of your inputs. So this is the basic idea of hierarchical cascade. Okay. So we can see this way. Whenever some input is coming to such devices or to such devices with this with the concept of this cascaded processing or hierarchical processing, there will be some wake up word or wake up some initial detection. Okay, this is not only, we will today discuss about something else also, one face detection algorithm. So there you will see how the stages are divided, or this wake up strategy is actually formed in some different way. This is not that always we are doing this wake up with some key word or key signal. So there will be, based on your application, you have to identify what may be your wake up signal or wake up input. Okay, based on that wake up input, the first stage processing will be done, and then the rest of the inputs will be passed or not passed based on the classification strategy going on in your first level inputs. And then from stage 2 to stage 3 and stage n and so on. So this is the basic idea of general hierarchical cascaded system. we have to see whenever we are defining these type of, cascading or hierarchy we are incorporating, what are the typical operators or features we have to consider in each stage to make this hierarchy meaningful, to make this hierarchy acceptable. Okay. So this system typically do not expand upon this approach outside of two-stage hierarchy. Okay. In general, what happens in for very why it is written? It is very for very comparatively simpler operations, simpler applications. There is two-stage hierarchy. First one is the wake-up stage, and the second one is the actual classification or the detection. But in multi-class scenario, as we proceed, we will see with some examples. These stages will be more. These stages will grow based on the type of application you are handling, based on the nature of the application. That's why we are telling that this example is basically related to this third part. We are exploiting the application level characteristics to increase the energy of efficiency. Okay. So we will come to this feature later. First, we take a few definitions and together we will come back. We will see these features. Okay. With the example, we will see this. So as you understand that we are dividing the functionality basically into multiple stages. Now, when we will evaluate the whether my stage, if this stage is acceptable or not, we have to uh, consider a few parameters. So for that, we need to understand few definitions. These parameters will be we will keep associated with each and every stage starting from our wake up stage, and we will check these parameters, and based on that we will check whether the hierarchy we have designed, the way we have divided our functionality, the way we have chosen the number of steps, chosen the number of stages, whether they are acceptable or not. And these features or these parameters are, first one is recall. I will come one by one to this definition. Another one is pass on rate. Okay. And another one is misclassification, probability of misclassification. Okay. Maybe in general machine learning also this recall, pass on rate you have already learned. So we will take this parameter, revisit these parameters once again, because we will actually map this with our data. And then we will evaluate whether the hierarchy is okay to accept or not. Okay. So the first one is recall. Recall is the probability that an instance of a given class I, you can see here, instance of a given class I is classified correctly in stage n or not. So whenever you can see here in that hierarchical framework, whenever we are defining recall, we are defining it with two parameters. One is Rn with the parameters are n and r. So n defines the class for which we are talking about this recall, and r defines the r indicates the given class for which we are computing the recall. Okay. So this is basically the probability that an instance of a given class I is correctly classified in stage n or not. Okay. This is a very standard definition. Maybe you have also studied in multi-class scenario, and we will see how it is related to our framework. Next one is this pass on weight. This pass on weight is a probability that an instance of class I gets passed along to the next classifier by stage n. So again, pass on weight, if you see here, it is associated with to this stage as well as the class I. Okay. So for a particular stage n, by pass on rate, we are giving the probability, it is a probability that an instance of class I, whether it is getting passed along to the next classifier. Now you will, okay, first let's define this misclassification, then we will come back again to these definitions, pass on weight and misclassification, and what we will see what is significance of this. On the other hand, this pass on weight is the probability of an element of class I to be classified as a pass on class. Okay. Now, misclassification is the probability of misclassification of a sample of class I as class J for a given stage. So again, for a given stage, whether the classification is done correctly or not, whether that a sample of class I is correctly classified as, correctly predicted, classified as the member of class I, or it is misclassified. From there comes the probability of misclassification, that whether the a sample of class I is misclassified to the misclassified as a member of class A at a given stage. Okay, so this is the meaning of probability of misclassification. Now, when we are talking about hierarchy or this type of hierarchical processing, we will see what is the significance of this. Okay, so let's say you have maybe let's come to this diagram what we have discussed. In this wake up stage, you have set some parameters, that this is my wake up signal, and after that your classifier is active. Now come to, let's say, stage 2. There you have done some classification. Maybe as we will take the example of our face recognition technique, there we will see that their classification is for identifying some faces from the background. Okay, not only in voice detection. So far we have only talked about, okay, Google, Alexa, etc. Let's take this other example also. Here, this face recognition. Maybe you all have seen, if you open your Google Photos, nowadays they club together few faces, and the identity, if you select a particular face, they will show the images related to that particular face. Have you seen this feature? Anyone?
Yes, ma'am.
So this is the one example when they are actually using this type of hierarchical cascading, and that these type of processing. We will see with that face recognition example. But you can think in this way. In maybe in the stage 2, in the first stage, in the wake up stage, what they can do. Your application is to do face recognition. So that means if there are some images, you're having multiple images, and where maybe the faces are in some background, maybe some images of sky, trees, and other background. So in the wake up state, it is only classifying that whether that particular part is an image of a background, or it is a face. So only that much. Maybe that is the wake up requirement. So that's why I'm telling this. Whenever we are deciding this wake up factor, it will be typically you have to analyze your algorithm, and it is algorithm sorry, so it is application specific. The application you are choosing, based on that you will choose your wake up strategy, where in voice specific examples, voice specific mls, wake up strategy is something like this type of keywords. In image detection, generally this wake up part deals with this background isolation. Okay, so after that, then you are in stage 2. Maybe you are just trying to identify human face. Okay, maybe in stage 2 you have classified, you have removed all the your pass on class will be all the class members will be the human face. Okay, and all other cat face, dog face, everything will be rejected. That means they will not be passed as a member of the class, pass on class. So that means pass on class, that you are deciding that what to pass to the next stage. That means on what, on top of what data, what input image, or not always input image. For this face recognition, that will be input image. For that type of Alexa, okay Google related example, those will be input keywords, not input keywords, the some other type of keywords. So which type of information you are passing to the next stage, that is the stage 3, that will decide your pass on class as well as your pass on rate. Okay. So pass on rate is the probability of an element class I to be classified as the pass on class. You are you are actually trying to pass this information to the next stage, and that's why you are making that information as the member of this pass on class. Okay. So the same thing what we talked about just now, this the values of recall rate as well as pass on rate depend on the use classifier in the stage and from its operating point. Okay. So these are both design choices. I think so far you have understood, and it will vary application to application. Okay. Similarly, when we come to this misclassification also, this misclassification, when it is very important to understand when this type of misclassification is too costly, or we must say too dangerous, or when it is not so impactful. Let's say you have, there are two things, there is a class A and class B. Okay, and this class B is your pass on class. Like we have taken the example of our face recognition. There we have one class related to background, maybe background is our class A, and pass on class is your face. Now you have misclassified one background and you have classified it as other particular face, maybe face of a cat or dog, and you have misclassified it and made it a member of your pass on class. That means an element of a member of class A has been misclassified to class B, where pass on B is the class on pass on class. Now this situation is, of course, is a misclassification. It has some impact. What is the impact? That you are passing this information to the next level classifier in the stage 2 classifier or stage 3 classifier, and there some again classification strategy will be applied to this information. So there will be some again some operation to classify, to accept or reject this input. So there will be some extra operation, but it will increase your amount of energy consumption. It will make your operation costly. That's all, nothing else. So if you have misclassified anything and made it a member of the pass on class, this make your operation costly in terms of energy consumption. But it is not so detrimental, because in any way that information is getting passed to your next stage, and it is again getting a chance to be classified, and it may happen in the next stage it is you are classifying it correctly and it is getting rejected because it is not anyway human fed. So it is when we are dealing with more intrinsic features, it is getting rejected. But if the reverse scenario is there, that the some information is supposed to be the member of this pass on class, it was supposed to be get classified and to be to get incorporated as a member of this pass on class, but you have wrongly classified that to as a member of this class E. So if this is the situation, this part is more detrimental, because you are actually removing, you are rejecting some legitimate data to be passed on, and maybe that is carrying some important information. So this is, so misclassification, it may happen. This it has some, and I mean the effects in which way you are misclassifying data. it is very tricky and it is very important to understand, because if the misclassification are happening, that you are incorporating something wrongly in the pass on class, that is costly, but it is not so detrimental. Whereas if you are the reverse thing is happening, reverse condition is appearing, then the situation is detrimental and there is significant amount of information loss. Okay, is this point clear about this pass on rate and misclassification? Everybody, is it clear? Are you there? Am I audible? Yes, no?
Yes, I'm audible.
Oh, okay. Is it clear, this part? Okay. No response. Then tell me. Yes, no. Should I repeat? Okay,
Ma'am,
you're
I had
silent.
one question.
Yes, tell me.
Ma'am,
Yes.
how will these probabilities will be calculated of the classification and misclassification?
Okay. Okay. So this is
Hello.
everything. Yes. Hello. Yeah. Okay, I got your question. How this can be calculated, right?
Yes, ma'am.
Yes. Yes, I'm coming. Any question? Any other question?
No, ma'am. Only this.
Okay. See, everything we are this part, everything we are talking in terms of training domain. Okay. In training data, you have some already have some what to say. You have some data, and you know their particular actual class, which you can think in this way. You have some training. Sorry. When we are talking about any ML classification technique, we have two parts. We are talking about supervised learning, and we are having one training data set. Okay, this is my training set data set, and we know this is the actual class. Actual class. Okay, this is my training data, and you have some features. Feature one, feature two, feature n, like this. Okay, you have some values 0 1, or some way you have stored these values, maybe some in a form of some vectors, a matrix. These features are stored, and based on some features, you know what is the actual class. Okay, based on maybe you have two classes, 1 0 1 0, that way you have the information. Then you have decided one cascaded technique. You have planned some wake up strategy, some algorithm, some steps. Then you have planned some stage one, stage two. There also you have developed some models, that some learning and prediction steps you will do. Those steps you have decided. Based on that, you in the this entirely we are talking about the training phase. Okay, in the training phase, we are applying our design framework, our design algorithm steps on this training data. Okay, and we are checking whether we are getting the some predicted class. This is the predicted class. Predicted class. Okay. Now we are checking that, and from there, if you are getting these two information, this predicted class and that actual class. Now, can you calculate this one?
Yes, ma'am.
Now you can calculate, right? That when you are having these two informations, you can check whether your the whatever algorithm you have designed, the steps you have designed, those steps, those model. Actually, whenever we talk about machine learning, what we do, our main motto is to design the model. whether that model is correctly mapping these feature inputs to the particular class value or not. If it is classifying correctly, you are getting some recall probability. Your probability related to this recall. If it is not, you are setting the value accordingly of your recall. And this pass on rate also. Is it clear? No?
Yes, ma'am.
Yes. Any more question? Any other question? No. Okay.
And in this
Yes.
pass on,
Yes.
hello?
Yes. Yes. Tell
Yes,
me.
ma'am. In pass on rate, it is the probability of instance that cache pass to the next classifier.
Yes.
But uh, isn't it that an instance will always be passed to the next classifier
No.
if
No.
it's
That's what.
passed?
Okay. Okay. Again, come back to the example. Okay. You have some images. Those images are, let's say, in your Google Photos. Okay. You are trying to search only the photos, only your photos. Okay. You maybe you're having many friends and you have uploaded their photos also. Now, when in your wake up or forget about any stage, pass on class or pass on Z is true for any stage. In that stage, you are just trying to classify the images with you or will it, I mean, your images, your face. That is, if your face is there, then only you are passing those images, those inputs, or those information to the next stage. If for all other images that is containing maybe your friend's face, that is containing maybe some background, some scenery, whatever it is, you are rejecting there. They are not being the member of that pass on class. So based on that, you are calculating this pass on rate. Is the probability that an instance of class it gets passed along to
Yes,
the next classifier. Okay, is
yes,
it
ma'am.
clear? Yeah, yeah.
Yes, ma'am.
So that way, that is the, I mean, the concept of person rate. It's basically person rate. To understand that, you have to keep in mind about this person rate, person class itself. And if that is so, from there you can get the idea of misclassification, whether it is getting classified correctly or not. Okay. Anything else?
No, ma'am.
Okay. Any anyone else? If you want to ask any question, okay. Then come here. So this is the example we are taking. Okay. This is one system, overall system. Consider they are divided into this n stages. Okay. This is 0 to n, or maybe 1 to n. Okay. The n task of the system is assumed to be complex multi-class classification task. Why it is so? In the n task, let's think again, come back to the example. Consider the face recognition example. Initially, the wake up state is simple. It is only classifying whether it is coming or the images are related to some background or some human face. So that is only the classification. Now, in the end class, maybe you are trying to get this classification that the images actually the way you just go click your Google Photos, you can see this example. They give you the classification. They identify few persons maybe with whom you have more pictures. So maybe you, your father, mother, some close friend. So that way, maybe 4 5 persons of photo, you can click one of them, and related to that you can get all the images. So basically, when it is coming to that final class, it is a multi-class classification where they are classifying those images according to those class requirements. So they are, though the classifier is classifying that whether the image belongs to you or your father or your mother or your close friends, like that, this multi-class classification is coming into picture. So when you are talking about the first wake up stage, it is very simple. But as you are going deeper, you can think in stage 2 or stage 3, their exact features. In stage 2, you have already identified whatever inputs you have got, they are only containing the human face, or I mean uh, only the only the human face. Now you are actually focusing in maybe the stage 3 or stage 4. Those are your last or final stages. There you are focusing on more intrinsic features. You are focusing on how, what the feature of your eye, feature of your ear, or your intrinsic feature. Then only you can classify those images where only you are present. So the more you are going deeper, the advantage, what is the advantage of this hierarchy? That the more you are going deeper, the more you are focusing on the detailed features, intrinsic classification, costly classification, complex classification. But what is the advantage? The advantage is that you are dealing there with some less amount of data. You have already chopped off the background, chopped off your other friends, chopped off your other related images. You have only focused. You know, in that class, the final input, whatever you are getting, final pass on class, whatever that is, that is coming from the previous stage. You can actually use this term now, that the pass on class, the information it is contained, it is very much restricted. It is already pre-classified, and it is containing some related data that is useful for your final complex classifications, final feature, intrinsic feature detection that you are going to do in your last or final stages. Okay. So this is the, I mean, this is the way the layers are defined. That whatever you are doing in the first stage, first class task, again it is written the same. First task is typically a binary wake up detector. This wake up detection, maybe as I have mentioned, that it may be, it will be varying application to application. But whenever a typical hierarchy proceeds, the classifications will get complex, and it incorporates more costly, more complex features. Okay. As it is written, the typical hierarchy starts with a simple binary classification that removes the most obvious negative samples, such as background image and noises. Okay. But as it proceeds, it handles with more complex features, but on lesser amount of data. So the advantage is here, cheap stage, it is always on, but it is doing some simple classifications. Whereas this expensive stage, it it is sporadic on, it becomes on when it is getting some valid pass on class from the previous stage. Okay, that's why we are saving that expensive this multiplication, where you need to have very critical filters and very small strike, and you are doing constant filter weight related multiplication. Those multiplication is actually obvious, you have to do it, but it is coming in these final stages where you have already chopped off the most negative samples, the obvious negative samples. Those have been already detected, or those have been already removed. So these type of costly filter multiplication, filter operations, you are again not doing on that negative sample. Okay, so this processing step. We have whatever we have explained with the example. So the positive class in this framework is called the pass on class. Pass on class means whatever information you are actually, the members forming pass on class, which you are actually going to pass to the next stage of the hierarchy. Now, in this case, maybe this one also a very standard, I mean, concept from general machine learning. Most of you know. Still, I'm repeating once again. This is the concept of true positive and true negative. And since we have already talked about the word recall, or we will be talking about precision, so it is better to have this idea about true positive and true negative. Okay. Now, when you have selected some item, okay, as we have, this is also very much related to the word misclassification. We have talked about the probability of misclassification. So whenever we are predicting. Maybe you I think you all understood that we are mostly concerned about this POC here, pass on class, because pass on class, whatever we are classifying as a member of this pass on class, that is only getting transmitted, that is only getting passed to the next stage. And after next level processing and the final decision making is only we can it will is only get affected based on what we are actually passing on the pass on class of each class. Okay. Now maybe you have selected something as a positive. That means true positive means you have identified something as a member of pass on class. That is your positive class, and you have identified predicted a value a member as a class member of this pass on class. Then there are two things can happen. There are two possibilities. One is whatever you have classified as the member, maybe your input M. This member you have classified as a member belongs to the pass on class that you have predicted. This is based on your prediction, mind it. Now there are two things can happen. One is truly this M is a member of your person class. That means truly this M is a face. I mean image of a face. Maybe it is a human face, or this is a part of a background that you have wrongly classified as the member of this person class. So whenever you are classifying this M as the member of person class, and in reality also M is the member of this person class, then we term it as true positive. Okay. But when that is not the case, that means maybe M is a face of a dog, and you have classified that, predicted that as a face of human being, and you have considered that as a member of that person class, then that is called the false positive. Okay. Okay. So that means the members you are forming, the number of elements you are putting in the person class, they are maybe truly true positive, they are the outcome of true positive, or they are maybe the outcome of false positive. Okay. Similarly, whenever you are not classifying something, from there comes the concept of true negative or the false negative. Okay. That means false negative means what? False negative is the most critical scenario that I already explained. That means you have classified something not the member of this person class. So that negative that is not selected, that is rejected and considered to belong to the negative class. But in actual case, that is maybe the M dash, that is actually the member of person class. That is the actual case. But member M dash you have predicted not as a member of person class. That is your predicted result, predicted outcome. Now this scenario it is called the false negative. Okay. So based on that, whenever you are defining that recall, you are basically, this recall is the ratio between the true positive and the predicted result, or true positive and the ratio between the true positive and true positive plus false negative. Okay. Similarly, the precision, when we define the precision is the ratio between this true positive divided by true positive and false positive. Okay, so whenever you are considering this precision, you are considering all the true positives and false positives. Among them, you are taking this true positive only. In case of recall, just this is the change. This part is the change. You can see the change. In recall, you are considering the true positive as well as the false negative. Among them, how many of them are the true positive? And then comes the accuracy. This is the true positive plus true negative divided by total. So these two we will be, I mean, we generally discuss more and we generally refer more when we evaluate any stage or how my classifier is actually working in a particular stage. When we try to evaluate that, when we try to understand that, this precision we call these parameters, we actually evaluate and we check whether my proposed algorithm, proposed architecture, whether it is working fine or not. So this, whenever you are defining this recall or precision, so this concept of true positive and true negative, just keep in mind and just think a bit for your application, which one is dangerous. I mean, why this false positive and then false negative? These things, how they can contribute to be to the information loss or your, I mean, reduction of your accuracy. How these parameters can affect. Okay. Okay. So now maybe you have some idea that what we are doing, the processing step, what are the steps, what we are doing. So that you have the idea, right? So we have basically we have our application. Based on that, we have the idea of our functionality. That functionality we are dividing into multiple stages. In for each and every stage we are trying to evaluate these type of a few parameters, and we are checking whether we are getting high true positives or not. That is our objective. That of course we do not want to lose in terms of accuracy. We want to maximize our recall. We want to get maximum true positives. So that way, whether our architecture is working fine or not, or do we need to make any change in the assumption how we have divided our stages. So that part we evaluate in for every framework, for every application, or for every exam. Okay. The same thing we are going to tell here that whenever we are trying to optimize our hierarchical cascaded framework, our system, so we are trying to compute our total cost and the recall. Okay, total cost means cost here. What is the cost in terms of what? Can anyone tell me? Anybody? When we are trying to compute the total cost, we are trying to minimize the total cost. What cost maybe we want to minimize? Nobody.
Power, but energy.
Power or energy, right? And how can you minimize that energy?
By making sure that the number of activations of the later stages are as minimum as possible.
Yes, that means you are trying to reduce the number of operations in each stage, right? And that way you are restricting the inputs or in the members or the you are uh, you are trying to maximize the true positives, but you are trying to restrict the number of members in the pass on class so that you can restrict the number of operations in each and every stage, and that way you can actually restrict the energy consumption. But in whatever you do, you don't want to compromise in terms of recall or accuracy or precision of your design. Okay. So that way we have whenever we are specifying a stage, we are keeping these parameters in mind. We are keeping considering the parameters, its cost. We are considering the recall. We are considering pass on rate, and these are known. So far we have understood. Okay. Now we will see once we with the one example framework, When we have only considered this recall and this pass on rate and we tried to minimize the energy, few important observations we have found: the statistics of the input data, okay, and the probabilities of the occurrence of each class, how they are also affecting our decision making. Like how many stages I will choose. The actually the next important question comes into our mind. Okay, I have understood that I will divide my functionality in few stages. Now, first thing, how many stages I will choose? In what basis I will decide that? So for that, one experiment shows that how the statistics of input data and the occurrence of this class, so these probabilities, how they're influencing. Okay, we'll see that one by one. Okay. Now, just a deeper thought with this diagram, that we have understood this one, that we have some key stages, that is our first level stages, and then we have some our expensive stages that will be in the form of mode of sporadic on, not always on. And when we are defining each stages, you can see here, this is the for the class 3 class second stage, this is the second stage, and this is the this stage is having only 3 class. So all in each of the stages, it may have some single binary classification, or it may have you may consider some multi-class classification based on your application requirement. Here, the example it is shown that in the stage two, it has 3 classes. For each of the class, basically, you can see here you are computing this recall rate, you are computing this misclassification possibility, probability, and this way you are actually fixing those parameters. And your objective is to process, I mean, settle the processing amount in each stage in such a way that you will maximize the recall, you will maximize the true positives, but optimizing the energy, optimizing the cost related energy related to the cost, cost related to the energy as far as possible. Okay. So basically, for each stage, we form this type of matrix. This we term as confusion matrix, and based on that, we actually check what will be the value of our recalls and this misclassifications for a given amount of energy. Okay. So based on that, we can actually compute this total global cost. Okay. This global cost, you will see, this is the cost for the first wake up stage. That is, in general, it is not dependent on the pass on rate. So we have kept it separately. Next, all the classes you are considering for 1 to I, you are considering the probability of occurrence of these classes and the cost associated with the classes and the pass on rate. Okay, so if there is a pass on rate of based on the pass on rate and the probability of occurrence, you are computing the cost associated a particular class and you are adding them up along with your the cost of your wake up state. By that, by this computation, your calculation, you are getting the total cost associated with your framework. And this total cost, what you want to do for a particular level of cost, this CN, for a particular stage, you are trying to reduce as far as possible, or at least when you have chosen some existing processor, you know how much maximum cost you can support. And based on that, you are checking what will be your recall, how many true positives you are finding, how many machine learning related this type of multiplication or operations you can actually do. This global cost and this recall rate will give your estimate. Similarly, for that this recall rate, this is again dependent on the pass on rate multiplied by the recall at the stage of that class at that stage. Okay. So that way you are computing this final recall and considering this, as we have already mentioned, this is not the exact relation or exact value of your precision. Okay, this is just they have given to show that whenever your true positive will increase, your recall rate will also increase. And so on that, whenever your true positive will increase, your precision will also improve. From these definition also you can get the idea. So in turn, your objective is to maximize this recall or the precision, minimizing, yes, this is your final true objective. This is your true objective optimization problem. This is what you want to do. You want to minimize the cost as far possible, your total cost. Now you know how to compute them. Now you know how to compute this recall value. This recall value, you can see this C, P, and T. C is the stage level cost, the class probability, this P, and this tau. This tau is a discriminating the particular threshold. What we mean by this defines the operating point of a given classifier. That means this threshold defines that for your these are the parameters related to your classifier, that up to a certain value, below a certain value, it is not acceptable to you will not accept that classifier. Maybe that threshold is related to your accuracy, or that threshold is related to your how many true positives you are expecting. So based on that you have set some threshold, and that is the parameters you are considering when you are computing this recall, as well as you are computing the cost also. Okay, so this is the Cn is that every cost is associated with a specific classifier in a stage. The tau it determines the operating point of recall and the pass on rate, and n is the number of total stages. So based on these parameters, finally when you have identified your functionality, your application in such a way, okay, you can divide them into some different stages. So for each and every stage, you will basically compute the recall, how many true positives you are getting out of the denominator, and to get that to the high recall to maximum recall, what is the cost associated with it? Okay, so next, this is a system description. You can go through it. Here they have what they have done. They have done a full 256 class classification. Okay, and the steps are the same what we have already discussed. The cascade was composed of n configurable stages. We will see what will be the value of n and how this n will vary based on certain parameters. We will see with the example results. Okay. In each stage, an optimizer will choose an optimum classifier and its operating point. That means the threshold that we have mentioned. In each step, multiple classifiers are modeled. That means in each step, you are having multiple classifiers, and based on that, you have identified the number of stages. Okay. Now the values are given, and the cost increases exponentially. That we already know from stage 1 to 8, as the complexity of the classification task also increases exponentially. So this is a relation they have given based on their application, but it may change. It is not that exactly this relation will hold good, but the cost will increase as you go deeper in your framework. Okay. Now we will come to one, and with this stage, with this framework, they have done one interesting experiment where they have shown that for that framework, not only the insights of the design that is meaningful. That means not only it is important to know how many operations I'm doing in the each and every stage. So far, that was the concept, right? That only we have focused on the number of operations, and from that we can actually get the amount of energy that is required. Another important factor that was observed, that is the input statistics. Okay. So to estimate the impact of input data, there four different cases were considered. That means they have actually changed the distribution of the input. They have used some data sets, that is, one is uniformly distributed, one is medium distributed, skewed, and highly skewed. Okay, so you can see these are the PDFs, I mean probability density functions of those data. But the interesting observation you can find from these data, I mean this table, when you are having this type of, these are the distributions. Okay, these are the distributions. So for each distribution, mm, irrespective of the size of the records, okay, high, medium, or low, you can see one trend, that the trend was observed that whenever you are using uniform data sets, the number of stages required, you can see here, you are getting always the effective activations at this 5 or 6 or 7. For each case, maybe it is a record number of records high or medium or low. Here also again you can see for uniform uniform data set, you will get this. Here also you will see this. See, whereas if your data is extremely skewed, you are getting this output or classification from some initial lower number of stages. That means the idea is, if your data is highly skewed, it's the same for all of them. The idea is, you can see here, you can revisit here the details written. The optimal hierarchy, it is given that it varies from 3 to 8 stages, that is specific to their experiment. Select the stages in the optimal architecture with minimum cost. But here also you can see, okay, before that, we'll finish here. In a system with uniform input distribution and a high recall target, only the last 4 stages are used. Okay, even though they are the most expensive. That means whenever you are having this type of uniform distribution, the advantage of this hierarchy you are not getting. It is not. That's why we are talking this one as application specific. The input data statistics you are using, your the efficiency of your proposed framework will also depend on that. That means if your data is highly skewed, then you will get better results. You can actually use less number of stages and you can get better response starting from the lesser stages. Whereas if your data is not so skewed, it is uniform in distribution, that advantage will not be there. Okay, see, it is already written. This is because more samples can only get a correct final classification at the later stages. So data is uniformly distributed. So that way you are not getting actually the effect or advantage of this hierarchy or cascading. So far what we have talked about, that we are only from our functional point of view, we have only dividing our computation steps, and we are planning going for this hierarchy and we are deciding the stages. But while we are doing the experiment, one another feature comes into picture, that is the input data statistics. Based on what type of input data you are, I mean the distribution of the input data, that will also affect that how many number of stages will be actually important, and I mean from starting from which number of stage you will actually get the effectiveness. Okay. So this way you can see here, if you observe this 4 graphs, so these are the number, with the number of stages you can see the variation in the cost. Okay. And this variation, it was observed for uniform data, medium skewed data, highly skewed data, and extreme skewed data. And as you have the final target, that you are going to identify the number of stages, and you are going to have a, a significant amount of recall. Here you can see that these colors, they are varying in terms of recall, the percentage of recall. This green is 98% recall, red is 95% recall, and so on. And as we mentioned about the threshold, a parameter here, we talked about the uh, well, here we talked about this threshold. Okay, this this one. So you can see here this, when we are actually choosing this recall value, we are taking this, considering this way that we are fixing these values. This recall, this 65% we are considering that is low, medium 85%, high 95%, and based on that we are setting some threshold values that for which we will go for the cost calculation, or for which we will decide the number of stages. Below that, in spite of the fact we are getting some value that's of no use, whether it is not crossing the particular threshold. So that way, from these experiments, it was inferred that not only the number of computations, basically number of, I mean, input data statistics, that's also the deciding factor of how many stages will be required, or whether we are actually getting any gain by using this type of cascaded processing or not. Okay, so this is the, from there we are actually computing the optimal number of stages, as we told that based on our nature of our input data, we can actually decide the optimal number of stages. So these are our few observations that for the system of uniformly distributed input data, the shallow hierarchies are optimal. If the input distribution is skewed more, cost can be reduced by going to deeper hierarchies, filtering out more samples early on. Cost can vary up to 6 orders of magnitude. Actually, these values, I must say that this is specific to their example they have taken, the data set they have taken. Okay, the 6 orders or 5 orders that may change, but these observation is, this is basically true for if you take all other type of data set, other type of examples, other type of domain also in your respective domain. If you want to apply this hierarchy or cascading related concept, and then you form the framework of your your this CNN processing or ML processing, then these orders will change based on the application. But this concept, this is universal, and this will hold good for most of the applications. Okay. So the from there, this is we have actually combined the overall observations. That is, we have discussed the influence of the performance goals and data statistics, and then the like noise background, when we can actually can remove in the early stage if these statistics are skewed and so on. These are the whatever we have discussed, that is the reputation. You can go through it. So here again, this is the example what we have mentioned, the face recognition hierarchy. The same, this whatever we have discussed, that was applied to this example concept. So you can see here one interesting thing is written, like when we are directly going to do this type of NN based large scale face recognition, what is the requirement of energy? Okay, and from this data you can actually understand that why it is not meaningful, or why it is not possible to go directly to this NN based classification directly in this always on devices. Exact figures are given, And that's why we are moving to this hierarchical processing, where at a particular time we are only focusing on the energy requirement of a particular stage. Okay, so when we do go for general this image processing, this is a pyramid scale concept that is computed by repeatedly smoothing and sampling. Then you are basically after doing this pyramid scaling, these are, you can skip this slides. I have just kept for knowledge that you are doing, this is the pre-processing part, this pyramid scaling. This is the only specific for image processing. But if you are taking your own example or your own domain specific problem or that application, there will be some pre-processing stage, but this is not exactly these type of scaling. So if you are someone is related to this image processing or you are just thinking about this application, you can just go through this. Otherwise, you can skip. Okay, basically here with the scaling, they are identifying the basic features and then they are moving to the next. Okay, so then we have answered that how many stages should be used in the hierarchy. For that, they have again used this input data statistics, and based on that, they have actually get the idea that how this number of stages may get affected or may change. The choice may get changed based on the input data statistics we are using. Okay. So here you can see this one. This is the background. So someone else was asking about this pass on class and pass on rates. So if you see, this is the background image. It is coming to this background. So it is not being the member of the pass on class. Whereas this phase, it is getting passed. It is a generic phase. It is getting passed. Generic phase. It is getting passed to the next stages, and it is being the pass on member of pass on class. It is increasing the pass on rate, and then finally it is reaching to this final stage. Here the next level complex processing is being done. Okay, so these are the stages they have shown. And in the intermediate stages, you will again that will again your application specific, that what type of features you are actually identifying. In this case, in this face recognition, they have actually chosen 4 stages. You can see here there are 4, n is equal to 4 stages. The first stage will be based on the first stage will be background detection, then it was owner detection, then it will be 10 faces detection, and then the final other 100 faces detection. So based on that, based on your application, you can actually choose what will be the intermediate stages and what will be your wake up concept. In that way, you can break your functionality into multiple stages, and each time you compute the recall and pass on rate, and your ultimate objective is to get a high recall value by minimizing the cost, energy related cost for each. So finally, this is the objective of our optimal architecture, that an architecture is optimal if it achieves the highest recall at a given efficiency in terms of process samples per operation. Okay. Optimize the full hierarchy towards minimal average cost per sample. Once all relations between the overall cost, pass on rates, and global recall are found, the hierarchy can be optimized towards the minimum cost. Okay. So finally, when you have got the pass on rates and the recall values for each stages, you can actually compute the final recall. You know the expression how to compute the final recall, and your objective will be to maximize that final recall and minimize the possible supported energy. And I must say, whenever you are having some options of these always on devices, so you have the knowledge that what can be the maximum support you can give in terms of energy. So that is your main cost value you can consider, and based on that you can fix that cost value, and based on that you can maximize your recall. That is the basic concept. Okay, so This is the main idea about this hierarchical cost processing. You can follow this chapter of this book. It is already uploaded in the drive. Okay, and tomorrow you will see one demo. Basically, your first assignment will be based on this. You will see some. Today we have talked mostly about this face recognition. Tomorrow you will see that there's a voice, this keyword recognition, and based on that you will develop one small application with this keyword recognition. Okay, tomorrow that demo you will see. Okay, so this is the basic concept of this wake up detection. Do you have any question? So you can see here someone are asking that for each stage they have actually some parameters models. For each stage you are defining the models, and based on that you are computing this person weight, person classes, sorry, person weight and misclassification probabilities, etc. Okay, is it clear? Anything you want to ask? Otherwise that's all for today. Tomorrow we will see demo and then we will discuss more on this.
Thank you, ma'am.
Thank you.